It is a uniquely modern frustration. You upload a photo to one of these incredibly advanced AI models, right?
Right.
Like maybe it's a picture of your living room and you just ask it for some basic design advice.
Sure, like where'd put the sofa.
Exactly. And the model returns this beautiful, articulate, paragraph-long response about, you know, color theory and spatial harmony and lighting.
They're very good at sounding confident.
You're so confident. And then right in the middle of this brilliant architectural analysis, it confidently suggests moving the large purple elephant out of the corner.
Which, of course, does not exist in your living room at all.
Right.
It just completely shatters the illusion of intelligence instantly. I mean, we call these visual hallucinations or content fabrication.
Yeah.
They are really the Achilles heel of multimodal large language models right now.
It's wild. It makes you wonder how something capable of, like, writing complex Python code or literally passing the bar exam can be so spectacularly bad at just looking at what's actually in front of it.
It is a massive disconnect.
And it's annoying when you're just rearranging your furniture. But if you scale that problem up to a self-driving car interpreting a busy intersection, well, that's different.
Oh, absolutely. Or an automated surgical robot looking at a live camera feed.
Yeah, in those cases, a quote-unquote purple elephant hallucination becomes a catastrophic safety failure.
And that is the exact tension driving the most cutting-edge AI research today. I mean, the stakes for multimodal reliability are just massive.
Which brings us to our mission for this deep dive. We have a genuinely fascinating state-of-the-art research paper on the table today.
It really is a game changer.
It details a brand new framework called Groc-PO that stands for Grounded Context Preference Optimization.
A bit of a mouthful, but a very important concept.
Totally. So we are going to figure out exactly why these AI models hallucinate when they look at pictures and how teaching them to essentially show their work, step by step, is completely revolutionizing their accuracy.
What's fascinating here is that the core problem isn't simply that the AI makes random, unpredictable mistakes. The real problem is about where those mistakes actually originate in its internal thought process, and how the current industry standard methods for training these models are, well, they're completely failing to catch those early errors.
Okay, let's unpack this, because to intervene in that thought process, we really have to look at the grading system.
Yes, the training mechanics.
The standard way we train these AI models to behave well is through a technique called direct preference optimization, or DPO.
Right, standard DPO.
And from what I understand from the paper, standard DPO has this massive structural blind spot because it only grades the AI on its final conclusion.
Exactly. It's essentially a binary grading system.
Like a pass-fail.
Basically, yeah. During training, you give the AI an image and a complex quotient. It spits out a full final paragraph.
Okay.
The training system then looks at that final paragraph alongside a human-verified perfect answer and basically gives the AI's attempt a thumbs up or a thumbs down.
So it's just comparing the final outputs.
Right. It's a chosen response versus a rejected response. The mathematical update to the model's brain only happens based on that final comparison.
That is so counterintuitive. It's like grading a complex multi-page calculus exam by only looking at the final number circled at the bottom of the last page.
That is a perfect way to look at it.
If the student gets it wrong, they have absolutely no idea if they messed up on step 1, step 2, or step 3. They just receive a giant red X.
Yeah, and in the AI architecture world, this creates what we call a massive credit assignment challenge.
Credit assignment challenge. I like that.
That calculus analogy really maps perfectly onto the neural network architecture. Because when you only penalize the final output, the model just doesn't know which of its billions of parameters to adjust.
Right, it's just guessing at what went wrong.
Did it misunderstand the complex logic of the prompt? Or did it fail to grasp the spatial relationship between the objects?
Or did it just misidentify a shape right at the beginning?
Exactly. Did its vision encoder simply misidentify a shape in the very first millisecond of processing the image pixels? Standard DPO literally cannot distinguish between those failures. It just tells the model to try again.
There is an incredible motivating example right at the beginning of this research paper that brings this whole credit assignment challenge to life.
Oh, the skateboard example, yeah.
Yeah, so imagine a photo of a skate park. There's a boy on an electric skateboard catching some air.
Classic action shot.
Next to him on the ramp is a man, and the man is holding this small black remote control, which he's clearly using to trigger the skateboard's motor so the boy can complete the jump.
Right, and there's also a yellow dog just hanging out in the background.
A very important dog.
Naturally. It is a very dynamic scene with a lot of moving parts and, crucially, a lot of inferred human intent.
So you ask the baseline AI, what is the man on the right holding, and what does this suggest about his intention?
A standard reasoning question.
The AI processes the image and outputs, and I'm quoting here. The man is holding a camera, and his intention is to film the boy's jump.
And under the standard DPO grading system we just talked about, that final reasoning is marked as a rejected response. The model is penalized for failing the reasoning test.
But wait, if we pause and look at why it failed, the reasoning itself isn't actually the problem.
Exactly.
I mean, if a guy is standing at a skate park pointing a small black device at a jumping kid, and you genuinely believe that device is a camera, then concluding he intends to film the jump is perfectly sound logic.
It makes complete sense. The AI failed because in the basic perception stage, its visual encoder just misread the rectangular shape of the black remote control.
So it hallucinated a camera.
Right. It committed what we call a grounding error. It failed to ground its internal reality in the actual pixels of the image.
Ah, I see.
The vision language architecture took a probabilistic shortcut. It saw a skate park, an action sport, and a black rectangle in a hand. And its language model side just statistically guessed camera.
Because cameras are at skate parks way more often than remotes.
Exactly. That word appears next to skate parks in its training data far more often than remote control.
But if that initial glance is wrong, everything downstream is just poisoned. The logical chain was doomed from the start.
Which introduces the core discovery of this paper, error propagation.
Error propagation.
Yeah. When we look at the AI failing that skateboard test, we're actually watching a domino effect in real time.
The snowball effect of being just a little bit wrong early on. And I'm assuming the researchers didn't just guess this was happening conceptually. They actually measured the decay.
Oh, they quantified it beautifully. They used a baseline model called LLVAV 1.57b. That is a very standard, powerful, open-source multimodal model. It has 7 billion parameters. And they ran statistical experiments on it, using their new data set, isolating the exact moment the model makes an error.
And what did they find?
The numbers are staggering. If the AI makes 0 errors in the early grounding stage, meaning it correctly identifies the boy, the skateboard, the man, the remote, and the dog, its final reasoning accuracy on complex questions sits at 73%.
Okay, a solid 73%. Not perfect, but a highly competent baseline for complex inference.
Right. However, if the model makes just one single error early on in that visual grounding stage, its final reasoning accuracy drops to 54%.
Wait, really? One mistaken object and it loses nearly 20 points of intelligence.
It accelerates from there. If it makes 2 errors in that early grounding stage, its complex reasoning accuracy plummets to 33%.
Wow. At 33%, it is basically failing the test entirely.
Completely failing.
This tells us we aren't dealing with a reasoning deficit in these models, right? We're dealing with a perception deficit.
Precisely. This proves a structural limitation of how we currently build and train multimodal AI. Their final, embarrassing hallucinations are deeply rooted in basic observational mistakes made milliseconds after the image is encoded.
So the errors compound non-linearly.
Yeah, that is the exact diagnostic breakthrough. So the engineering challenge becomes clear. How do you intervene in that specific millisecond to prevent the first domino from falling?
Well, if standard DPO grading is causing the problem by only looking at the final answer, the fix seems obvious. You do what a good math teacher does.
Right.
You force the model to show its work, and you grade the intermediate steps individually.
This is where we move to the solution presented in the paper, the Grounded Context Preference Dataset, or GCPD.
Okay.
This dataset is really the foundation of their new Groc-PO framework. They decided to structurally break down the AI's thought process into 3 progressive stages.
Let's walk through these stages because the structure is really the secret sauce here.
Sure.
So stage 1 is object grounding. This is the absolute foundation. No complex questions are allowed at all.
Right. Keep it simple.
You literally just prompt the AI to list each entity in the image and its key attributes. So for our skateboard picture, the chosen platinum standard answer is simply a boy, a skateboard, a man, a remote, a yellow dog.
Yeah.
That's it, just establishing the physical facts.
You are forcing the model's neural pathways to anchor themselves to the visual reality before the language model is allowed to do any creative thinking or statistical guessing.
Love that. Then we move to stage 2 contextual grounding. Now we start looking at relationships.
But there's a trick here.
Right. Crucially, we carry the correct answers from stage 1 into the prompt for this stage. So we ask, what sport is the boy doing? And the answer is skateboarding.
It is taking those isolated objects from stage 1 and integrating them into a cohesive action or a spatial scene.
Finally, we reach stage 3 grounded reasoning. This is the complex stuff. We keep the verified context history from stage 1 and stage 2, and we hit it with the hard question.
The original skateboard question.
Exactly. If the boy loses balance, who is most likely to help first and why? And the chosen human preferred answer is the man is closest and watching him, so he can react fastest.
Notice how different that process is from asking the complex question cold. By stage 3, the model has a verified, sequentially built context to rely on.
It isn't guessing what the black object is anymore.
Exactly. That was settled in stage 1.
I look at this 3-stage process, and I have to push back a little bit on the mechanism, just playing devil's advocate.
Okay, let's hear it.
When I first read this, my immediate thought was, aren't we just throwing more data at the problem? I mean, we already feed these multimodal models billions of parameters and terabytes of scraped internet data.
That's a fair question.
Is breaking a question into 3 stages actually doing anything unique neurologically for the model, or are we just giving it a thicker textbook to memorize?
The researchers actually anticipated that exact critique. They set up an experiment to prove that it is not about the volume of data at all. It is entirely about the structured cumulative sequence. They created a baseline test called flattened DPO.
Meaning they took the 3 stages and squashed them back into 1.
Exactly. They took the exact same 17,000 preference pairs from their new data set, the exact same volume of training data, but they stripped away the context history.
Oh, wow.
Yeah, they removed the scaffolding that carries stage 1 into stage 2 into stage. They turned it back into single stage, isolated question and answer pairs.
Let me guess. Without the sequential scaffolding, the model just reverts to its old habits, probabilistic shortcuts take over, and it starts hallucinating cameras again.
You nailed it. The hallucination rate shot back up to 61%.
61%.
Even with the exact same high-quality data, without the sequential history, the model's faithfulness just crashes. It proves that the AI must build the context sequentially. This framework actually mirrors the laws of human cognition.
That makes total sense. I mean, as humans, we don't look at a novel scene and instantly deduce complex physics or social dynamics in a single mental leap.
Right, we don't just jump to the end.
Our eyes sweep the room, we identify objects, we note how they relate to each other spatially, and then we reason about the future state of those objects.
We perceive, we understand, we deduce.
Groc-PO is forcing the AI to adopt a human-like cognitive rhythm. Okay, so we have our structure. But to train an AI to prefer a good path over a bad path using preference optimization, you need bad paths to show it.
Yes, the math needs contrast.
Right. You need a rejected response for every chosen response so the math can calculate the difference. Now, getting the chosen or good answers is relatively easy.
Sure, you just ask a smarter model.
The paper mentions using a super smart teacher AI, like a GPT-4o, combined with human verification to write the flawless stage 1, 2, and 3 answers. But where do the bad answers come from?
This is a crucial point.
Because if we just ask GPT-4o to write a bad answer, it might write something completely irrelevant that doesn't actually help the smaller model learn.
Exactly. The quality of your rejected answers entirely dictates how well your AI learns to navigate the edges of its own competence.
Here's where it gets really interesting. The researchers solved this using a technique called model-centric sampling.
I love this part.
Instead of having the genius teacher AI generate the bad answers, they force the target model itself, the smaller one they're actually trying to train, like LLMs, to generate its own bad answers for stage 3.
It's so smart.
Are they just like turning up the model's creativity, dial the sampling temperature so it hallucinates naturally, and then capturing those specific mistakes?
That is essentially the mechanism, yeah. They prompt the target model to answer the question, allowing its natural probabilistic tendencies to take over.
Letting it make its own mistakes.
Right. They generate multiple responses and then filter them to select answers that are structurally plausible but factually incorrect based on the image. It is a brilliant design choice for creating a custom curriculum.
It makes me think of, like, if you want to fix your golf swing, watching a video of Tiger Woods making a mistake won't help you as much as watching a video of your own specific bad habits.
That is exactly it. If the super smart teacher AI generates a rejected response, it might make a highly sophisticated, subtle error.
Right.
But the target model you're training might have a habit of making very basic, clumsy errors, like swapping a remote for a camera.
So by using the target model's own natural outputs as the rejected samples, you are pointing a mirror directly at its intrinsic failure modes.
You are capturing its specific tendencies to drop logical threads or hallucinate, and you are mathematically telling it, don't do this specific thing.
The math behind how they enforce that lesson is just as clever as the dataset itself. They designed a custom mathematical formula called the Groc-PO loss function.
The loss function is everything in machine learning.
Yeah, it's the ultimate judge, right? It calculates how far the model's prediction is from the correct answer and dictates how forcefully the model's internal parameters should be updated. And this specific loss function uses a dual weighting mechanism.
Right, because it doesn't treat every question or every mistake equally.
The first part is the stage-aware weight. The math automatically assigns higher importance to the later stages of our three-step process.
So stage 3 is weighted heavier than stage 1.
Exactly. The complex reasoning is heavier than the object identification. The logic here is that identifying a dog is a basic perceptual skill, but complex reasoning about who will catch a falling skateboarder has a much higher learning value.
You want the AI's gradient descent, its computational energy focused on mastering the hard logic.
Right. It dynamically tells the model during training, the basic perception is mandatory, but the complex logic is where you earn the massive parameter updates.
But the second part of the loss function is the real secret weapon, the hardness-aware weight.
This is where the training efficiency goes through the roof. It leverages the mathematical margin between the good and bad answers.
So.
Well, if the good answer is the man is holding a remote, and the bad answer generated is the man is holding a pineapple, the AI can spot the visual difference instantly. The probability gap is massive.
That's an easy sample. The model learns almost nothing from it.
Exactly. But if the rejected answer generated by the model is the man is holding a black camera, that looks dangerously similar to the truth.
Yes.
The model's internal probability scores for both answers might be nearly identical. That is a hard sample.
And this is where the genius of the loss function kicks in. The hardness-aware weight mathematically penalizes the AI more for getting the hard ones wrong.
Oh, interesting.
If the margin between the chosen and rejected answer is narrow, a mathematical multiplier kicks in. It forces the model to obsess over the subtle, difficult differences rather than wasting computational cycles on obvious, easy comparisons.
It is dynamically reallocating the model's attention. Instead of learning nothing from a million easy examples, it is sweating over the few hundred examples that actually challenge its perceptual edge.
Exactly.
The theory is just beautiful. We force the AI to build context step by step, we make it learn from its own bespoke mistakes, and we use a custom loss function to force it to focus on the hardest reasoning tasks.
But the ultimate question is, does it work?
Right. Does this structured self-correcting training actually move the needle on the benchmarks?
The data speaks for itself, honestly. They applied this Groc-PO framework to several open-source models, including LLV7B and 13B, and the Quinn 2.5 VL7B model. Across the board, Groc-PO absolutely dominates standard DPO.
And we aren't talking about a margin of error here. On complex reasoning tasks, specifically the LLaVA bench complex evaluation, Groc-PO achieved a massive 45% relative improvement over standard DPO.
It's a huge jump.
A 45% jump in complex reasoning just by changing how you structure the context during training is a total paradigm shift.
And crucially, it simultaneously pushed down the hallucination rates on specific industry metrics like MMHAL and AMBER.
For those not living in the research papers, MMHAL and AMBER are benchmarks designed purely to catch AI making things up.
Right.
MMHAL specifically looks for hallucinated objects that aren't in the image, and AMBER tests if the model contradicts itself generatively.
Usually in AI development, there is a trade-off. If you push a model to be more complex and creative in its reasoning, it hallucinates more.
But Groc-PO broke that trade-off.
Exactly. It made the models vastly smarter and vastly more truthful at the same time.
Let's ground those benchmark numbers in some real-world examples from the paper. There's a visual example they provide of a soccer match that perfectly demonstrates stage 3 reasoning in action.
I remember this one.
In the photo, player 10 is mid-kick, winding up to boot the ball. Player 7 from the same team is standing nearby, but he's just standing there, hands on his hips, totally passive.
Okay.
The prompt asks what player 10's action reveals and how player 7's stance affects the play.
A model trained with standard DPO looks at this image and outputs a very generic, unhelpful paragraph.
Right.
She says player 10 wants to attack,
Yeah.
and player 7 is just without active running, which might affect success.
Yeah.
It's so vague, it doesn't actually understand the spatial reality or the occlusion happening on a soccer pitch.
But the model trained with Groc-PO completely nails it.
Yeah.
Because it systematically grounded the objects in their spatial context first, it correctly reasons that player 10 is looking to pass the ball, but player 7's passive stance is literally blocking the passing lane.
It understands the physical consequence of the objects in the image.
Yes. It connects the visual facts to a logical, physical outcome.
There's another brilliant example with cows in the paper, too. It's a photograph of a herd of cows resting in a very lush green field.
Oh, yeah.
The complex prompt asks what this scene suggests about the farm's management and its future impact.
And the standard DPO falls right back into its text prior bias. It offers a hallucinated cliche, stating that the good management will bring the farm healthier and higher-yielding products.
It just guesses based on text patterns it read on the internet.
Exactly. It assumes cows equal milk products, even though there is zero evidence of dairy production in the photo.
Groc-PO, on the other hand, relies strictly on the visual evidence. It notes the cows are resting calmly, it notes the lush field, and it accurately predicts that the management practices will positively impact the herd's future well-being.
It doesn't jump to conclusions about milk yields that aren't grounded in the photo.
Right. It makes an evidence-based, coherent leap in logic.
And the researchers did something really clever to prove that the AI wasn't just getting lucky with these answers. They measured the token-level confidence using log probabilities.
Ah, yes. If we connect this to the bigger picture, a log probability is essentially the mathematical calculation a model makes before spitting out a token, or a chunk of a word.
Okay.
It scores every possible next token on how likely it is to be correct. If the model is guessing, the probability distribution is flat. Lots of words seem equally likely.
Like throwing darts in the dark.
Exactly. With standard DPO, when the AI answers a complex question, its internal log probabilities are very low. The distribution is flat. It is mathematically sweating.
But with Groc-PO,
the log probabilities are significantly higher across almost every single word in the complex response. The AI is actually highly confident in its reasoning because that reasoning rests on a rock-solid foundation of verified perceptual facts. It knows it's right.
which brings us to the ultimate takeaway. Why does Groc-PO, stage-aware loss functions, and model-centric sampling matter to you?
It's the big question.
It means the era of the multimodal AI acting as a fragile parlor trick is ending. We are moving past the phase where an AI can write a beautiful poem but completely fails to see the toaster on your kitchen counter.
Very well said. By forcing these models to securely ground their reality step by step, we are entering an era of logically coherent AI assistants that don't just talk smart but actually see the world exactly as it is.
Absolutely. This research perfectly solves how AI processes static images by building a sequential, flawless, logical context. But I want to leave you with a thought. Think about the implications for the near future.
Oh, the dynamic applications.
Yes. What happens when this exact three-stage framework is applied to dynamic, real-time video feeds? Imagine a self-driving car navigating a busy intersection.
That's a terrifying and exciting thought.
In that environment, the context isn't a static photo. It is updating every single millisecond.
Right. New objects, new relationships constantly.
If Groc-PO can ground reality this flawlessly and confidently in a single photograph, the leap to an AI systematically reasoning its way through a moving, chaotic, three-dimensional world might be much closer than we think.
It really changes the timeline.
From a skateboarder in a photo to a self-driving car in rush hour, step one is always the same: ground your reality. We will leave it there for today.